Hello, in this video we will talk about electron configuration, how the electrons are arranged around an atom, which has dramatic implications for both the energy of the electrons and, more importantly, for reactivity of the element. First, before we talk about electron configuration, let's review quantum numbers, which we talked about in the last video. So the energy of an electron and how it sits around the nucleus in an atom is described by its wave function, psi, and this wave function depends on four quantum numbers. N, the principal quantum number, gives you roughly the distance from the nucleus of the electron. L, the azimuthal quantum number, gives you roughly the shape of the orbital. The possible values you have for L go from 0 to 1 to 2 to 3, all the way up to n-1, and then we give these names. If L equals 0, that's an s orbital. If L equals 1, it's a p orbital. 2 is a d orbital. 3 is an f orbital. Alright, the next quantum number is the magnetic quantum number, m sub L, and the possible values this can take go from negative L to positive L, and this gives you the orientation of the orbital. And then finally, the spin quantum number, m sub s, is always either plus 1/2 or minus 1/2, and it allows you to put two electrons into a given orbital. So these four quantum numbers together provide an address, so to speak, for your electron as it resides around the atom. Now, the Pauli exclusion principle tells us that no two electrons in an atom can have the same four quantum numbers, and as a consequence, then we have to build electrons around an atom with different quantum numbers in order to get however many electrons we need around the atom. Here's a kind of pictorial overview of the principal quantum numbers on the left here, the azimuthal quantum numbers in the middle, and the magnetic quantum numbers on the right that give us the various possibilities that these can take. So let's start with this question. How many electrons can be placed into the 3D subshell? Alright, so when we say 3D, it means the principal quantum number is 3, then since it's a d orbital, it means the azimuthal quantum number, L, is 2. Okay, so if L equals 2, then m sub L can have 5 different values from -2 to +2. So that means there's 5 orbitals inside the 3D subshell. They have these names, 3D xy, yz, xz, z squared, x squared minus y squared. And each one of these orbitals can have 2 electrons inside, one with a spin quantum number of plus 1/2 and one with a spin quantum number of minus 1/2. And so we can represent this by drawing these little lines that represent each orbital. Underneath it we write what orbital it is, and then on top of it we denote how many electrons are in there by having 2 arrows. You can imagine that up is plus 1/2 and down is minus 1/2, although that distinction is not really important at the moment. Okay, so this is how we tend to draw electron configurations, and now let's use this as a starting point to then talk more about it. Okay, so if you have a single electron atom, so hydrogen, or helium that's a positive ion, something like that, your energy only depends on the principal quantum number n. And this is what we experienced when we talked about the Bohr model of the atom, that it only depended on whatever n was. You can go from the n equals 3 state to the n equals 2 state. It didn't matter what exactly existed within those states. Now, when you go to a multi-electron atom, something that has more than one electron, your energy depends on 2 things. It depends on the principal quantum number n and on the azimuthal quantum number L, which I can't make my pointer go over that far. That's sad. Okay, energy depends on n and L. So in the diagram that's on your screen, this shows you how the energy depends on n and L. So you have the 1s, you have the 2s, the 2p, the 3s, the 3p, and remember these are various combinations of the principal quantum number n, in this case 2, and then the azimuthal quantum number L, which L equals 0 is s, L equals 1 is p, so on and so forth. So let's take a tour through this. So down here in the 1s, n equals 1, L equals 0. M sub L also equals 0 because when L equals 0, M sub L also has to be 0. Alright, for the n equals 2 states, now we have a couple options here. L can go from 0 to n minus 1, so L can go from 0 to 1 in this case. And so we have two different choices here. And we call one of these the 2s when L is 0, and one is the 2p when L is 1. Now, for the 2s, M sub L only has one choice, it's 0. For the 2p, M sub L can take three options, from negative L to plus L. And so we have three different states here. And so we draw this with three lines next to the letters 2p that shows us that there's three possible choices here, three orbitals. Alright, the same is true for the 3s and the 3p. Now I'll talk about the 3d. N equals 3, L can equal 2, because that's n minus 1. And then M sub L can go from negative 2 to plus 2. And so there's 5 different choices here, which means there's 5 d orbitals that we get to talk about. Okay, and then so on and so forth. So how do you know the order of energy levels? How did I know to put 2p above 2s, vice versa? How do we know to put the 4s below the 3d? Things like that. So ultimately this is something that the Schrodinger equation tells us, but since we're not solving the Schrodinger equation in this class, then we just kind of have to memorize this order of energy levels. That said, don't freak out. There's a couple of very easy tricks that do a great job of telling you the order of the energy levels. So on the screen here I have one of them. And let me show you how to construct this diagram, for instance if you needed it on a test. So you start by writing 1s all the way down to 8s in a line. So we'll say 1s, 2s, all the way down to 8s. And then, off to the right, you'll write down which choices you have for orbitals. So in n equals 1, there's only the 1s. In n equals 2, you can have 2s or 2p. In n equals 3, you can have 3s, 3p, 3d. n equals 4, there's the 4p, the 4d, and now you have the choice of the 4f. And let me finish this out here. Okay, and here we go. Now something we haven't talked about yet is what happens after f. So typically we talk about SPDF as the orbitals we can make, but what happens after that is then you just go alphabetically. Then you could make a G, H, I, and a J orbital. Now it turns out that we never fill these other orbitals with electrons, but you can calculate their geometries and what they might look like, but you're never going to put electrons in them in the ground state. So generally you can just omit this part of the diagram. I just wrote it out here for completeness. Alright, so we made our little stair steps here, and then let's go fill electrons in. So now we start to go diagonally from the top right to the bottom left. So you'll start by putting an electron in the 1s, and then you come, trying to make a dotted line, then you come back up, that dotted line sucked, then you come back up here and then you fill an electron into the 2s, and then you go back up to the top. I'm just going to skip the dotted line part of this, and then you'll fill the 2p and the 3s. And by fill the 2p and the 3s, I mean that the energy levels of the 2p and then the 3s are lower than the other orbitals. So on the top of the screen here you have the energy levels from lowest to highest energy, and when you put electrons in those, they will fill up into these energy levels from the lowest to the highest energy. Because electrons, like all physical systems, want to be in the lowest energy state possible unless they absorb some extra energy somehow. Okay, so we fill the 1s, the 2s, the 2p, the 3s. Then you come back up to the top and you go down the 3p, then the 4s. And now you fill the 3d before the 4p. So this is where we start to get out of order numerically, right? So the 3d, then the 4p, then the 5s. Then we come back and fill the 4d, then the 5p, then the 6s, and then we come back and fill the 4f, 5d, 6p, 7s. And then finally we come back and we'll fill the 5F, 6D, the 7P, and the 8S. And now at this point, we've reached 118 electrons, and that is as large as the periodic table goes. So this is why we never fill the 5G, is because we haven't ever made atoms this big, that are bigger than filling the 8S. Actually, we don't even get past the 7P. So that's why you never have to worry about the G, H, I, and J. So in my head I call this the stair-step method. And let me get out of this drawing and show you the pretty book picture of the exact same thing. Okay, so you can do it that way to remember the order of these energy levels. And so now once you do this, then you have the order here, so then you can fill electrons in that order. So we start with the 1s. So if you're doing hydrogen that has 1 electron, you'll put that 1 electron into the 1s. And now we can write the electron configuration for hydrogen as 1s with a superscript 1. Alright, next one. Let's do helium. It has 2 electrons. Both electrons go into the 1s, so now you'll draw a right side up arrow and an upside down arrow in the 1s to show that there's 2 electrons in that same orbital. And then we'd write the electron configuration as 1s superscript 2 because there's 2 electrons in this 1s. And drawing the arrows up and down symbolizes different spin quantum numbers. Now let's do lithium, 3 electrons. Since each orbital can only hold 2 electrons, the 1s is full, so now we put an electron into the 2s. And then we'd write the electron configuration for lithium as 1s2, 2s1. Not surprisingly, when you go to beryllium, the 4th electron goes into the 2s, and here's the electron configuration for beryllium. Next one up, we get to boron. There's 5 electrons. One of those goes in the 2p. By convention, we put that electron in the farthest left 2p orbital, just because we read left to right and it looks pretty. There's really no scientific reason why we do that. Okay, so the electron configuration for boron is 1s2, 2s2, 2p1. And so the superscript numbers here tell you how many electrons are in each orbital. Alright, now when we go to carbon with 6 electrons, we have a question. Do we pair them first, or do we put the electron over to the right? And this is actually an interesting physical question. Do the electrons prefer to pair, or do they prefer to spread out across the orbital? And so this brings us to Hund's rule. So the most stable arrangement of electrons is the one with the greatest number of parallel spins. And the reason here is it costs extra energy to pair the electrons. Because they're both negative, they don't really like to take up the same space. So if we have these electrons parallel to each other in different orbitals, it's going to minimize the chance of electron overlap. Because both of these are the same spin quantum number, they cannot enter the same orbital, because then that would violate the Pauli exclusion principle, saying that you can't have 2 electrons with the same set of 4 quantum numbers. So if you make the spins the same, then they're forced into different places, and then that's lower energy because the electrons don't like sharing the same space because they're both negative. Okay, so we write the electron configuration for carbon like so. Now, when we go to nitrogen, there's 7 electrons. This goes in the 3rd orbital, still pointing up. And by convention, we do just draw the electrons pointing up first, and then we draw them pointing down. I think, again, just because it looks pretty. There's not a good scientific reason for why. Alright, so now when you go to oxygen, and this is, again, the electron configuration for an isolated oxygen atom, not for O2, which is a molecule. So here we're doing these configurations just for isolated atoms. For oxygen, it has 8 electrons, so that 8th electron would, now it has to pair because there's no other option for it. And so it's just going to pair really with any one of these. We just draw the far left one because it looks good. Here's the electron configuration for oxygen. When you get to fluorine, the 9th electron is paired. Here's its electron configuration. And when we get to neon, there's the 10th electron, and here's our electron configuration, 1s2, 2s2, 2p6. Okay, so then if you go look at this, the periodic table relates to electron configurations in a very critical fundamental way. So here's a chart of the outermost subshell being filled with electrons for each given element. So hydrogen, you put that into the 1s. Helium, it goes into the 1s as well, the last electron, really the only electrons. When you go to lithium and beryllium, the last electrons go into the 2s. And then when you go to boron, carbon, nitrogen, oxygen, fluorine, neon, the last electrons go into the outermost subshell, the highest energy subshell, which in this case is the 2p. And then you continue, and so sodium and magnesium, the highest energy electrons are in the 3s, aluminum, silicon, phosphorus, sulfur, chlorine, argon, you're in the 3p, so on and so forth. Potassium and calcium, scandium, titanium, vanadium, chromium, manganese, iron, they're all in here. So the periodic table is arranged by the outermost subshell that is filled with electrons, because that primarily determines the reactivity and chemical behavior of the element. Sodium, potassium, lithium, they all have just one electron in the outermost s orbital, and that leads to those pure elements being very reactive in a very similar manner, because there's just one electron in the outermost s orbital. So the periodic table was originally arranged by chemical properties, and then once we understood atomic structure and electronic structure better, now we can see that it's also arranged by electron configuration. So the nice thing about this is that instead of drawing out that whole stair-step method to remember the order of the energy levels, you can just remember the following about the periodic table. This block over here, you're filling all the S outermost levels. This block here, your outermost electrons go into the P. Down here, the transition metals, the outer electrons go into the D. And then the inner transition metals, or the lanthanide and actinide series, the outermost electrons go into the F orbitals. Now, one thing to note when you're looking at this is that n equals 1 is here, n equals 2 is here, n equals 3, however, as you're filling electrons, you'll go 3s, 3p, then you'll go 4s, then the 3d, then the 4p, then 5s, 4d, 5p, then 6s, 4f, 5d, 6p. Right? So you just follow along the periodic table, and then you can read the order of the energy levels from that. This is personally what I do because I find it to be a lot easier, but ultimately do whatever makes the most sense for you. And again, this explains how the periodic table should look, where the lanthanide and actinide series are inserted into the periodic table, because really what you do is you fill the 6s, then the 4f, then the 5d, then the 6p, just because those are the energy levels associated with each one of these orbitals. So I'll also put up on Moodle a little handout that has this periodic table with the orbitals drawn on it, if you find this helpful. It also has the stair-step diagram in the upper part. Hopefully that helps you understand the concept here. Okay, so there's the idea. Now, what kind of questions can I ask you about this? And generally I'll ask, what are the electron configurations of something, right? I have a little note in the top that using the periodic table for this might be easier, or you can use the stair-step method, or you can just memorize them straight up what the order is. So if you're going to look at magnesium, it has 12 electrons, and it sits on the periodic table right here. Now, what's the electron configuration of this? Okay, so as we go across, we see that we're going to fill through here first, so that's 1s, and there's 2 electrons in the 1s. And then we fill over here. Now the s orbitals are the ones you fill on the left side, and this is the second line, so this is then the 2s, and there's 2 electrons there. Then you go through these ones, and over here it's the p orbitals that you fill. And so this is the 2p, and you put all 6 electrons into that. There's 6 electrons there. And then now we come down here to the 3s, and then there's 2 electrons that we put in the 3s. So we say 3s2. And then this is our answer for what is the electron configuration of magnesium. Now let me drop my hand drawings, and I'll pull up what I have typed on the slide. And so you can either do it off the periodic table like I did, or you can somehow remember the order of the energy levels and then fill them in that order. Your electron configuration is down here. So you can imagine that when we go to heavier and heavier elements, this gets to be a giant pain in the bottom to list out all the orbitals like this. So what we can do instead is we can use the noble gas shortcut, at least that's what I call it, where you can take the electron configuration of the nearest noble gas, and not really the nearest, the most recent noble gas, going backwards in the periodic table. So when you look at magnesium, it's right here again, and so if you go backwards in the periodic table, the first noble gas you get to is neon. So you can take the electron configuration of neon, which is written right here, and then substitute that in to the electron configuration of magnesium, right there. So then this gives you neon, and you put it in these square brackets, and then after neon you have 3s2, so you fill 2 electrons into the 3s. So ultimately, I think this is a lot easier to do it this way, but it'll depend on what I say on the test as to what I want. If I say, just give the electron configuration, you can give either answer, either the one in purple or the one I'm just now outlining in purple, right? So you can give either one of those answers. Or I may say, give the electron configuration using the noble gas shortcut, and then that means I want this one. Okay. So while we're at it, let's introduce some terminology. I've already said this before, but I'll bring it back again. Valence electrons are the electrons in the outermost electron-occupied shell of an atom. And so if you write your electron configurations in the noble gas shortcut format, you can see that all of these are valence electrons for both magnesium and phosphorus, and then everything else are core electrons. So the valence electrons are the ones beyond the noble gases. And we call that the outermost electron-occupied shell in the atom. Now, this definition is not so useful for transition metals because, well, you're filling electrons into the 3D, but you already have electrons in the 4s, so that this definition kind of breaks down. But usually we don't use this definition for the transition metals. We use it when we're talking about the nonmetals over here, and then that makes a little more sense. So only valence electrons are the ones involved in the reactions and making chemical bonds. So that's why we really care about this number of electrons. We use this a lot in the chapter 7 when we start making Lewis structures. Okay, so some practice. So first of all, I'll do this one and then I'll let you have the next one as the quiz question. So what is the ground state electron configuration of lead? So pause the video, take a second to think about that, and then I'll put up the answer. Okay, so lead sits in the periodic table right here. And thinking how to do the electron configuration, we look backwards to the noble gas that's immediately preceding lead, which in this case is xenon. So we'll start with xenon and then work our way over to lead. So up here I'll start writing the electron configuration, and we're going to start by putting xenon in these square brackets to use the noble gas shortcut. Now, the first thing I'm going to do is annotate this periodic table. Over here on the left, you're filling s orbitals, and you start by filling the 1s, and then you fill the 2s, and then after you fill the 2p, then it's the 3s. And I'm just going to write 1, 2, 3, 4, 5, 6, 7 down the side because I find that helpful for me. Then now, over here on the right side, you're filling p orbitals, with the exception of when you're filling helium. And this row here corresponds to the 2p, this is the 3p when you start here, this is the 4, okay. Now, here you're filling the d orbitals, and now you start with 3 here, because the first d orbital you fill is when the principal quantum number is 3, because at this point you can have the azimuthal quantum number L equal to 2, because that goes up to n minus 1, so your L can equal to 2, and since s is 0, p is 1, d is 2, so that means you can finally fill the d orbitals starting with n equals 3. So a 3 goes there, a 4 goes here, alright, and then the last thing is down here for the inner transition metals, you are filling f orbitals, and for the same logic as why you start filling d with n equals 3, you start filling f with n equals 4. So this is 4, and this is 5. Okay, so now we've got this periodic table all marked up, and we can start thinking about how we fill electrons into here. So, starting at xenon, first thing we're going to do is we're going to put 2 electrons in the 6s. So I'm going to go up here and I'm going to write 6s2, because there's 2 electrons that went in there. Alright, so then the next thing we do, well, there's a little bit of 5d, but then pretty quickly we start filling the 4f. And so generally omit the fact that this particular periodic table shows you the 5d before the 4f, because we want to keep them all together, so we'll talk about filling the 4f, and then we'll talk about how we fill the 5d. So the next thing we do is we fill the 4f, and this has 14 electrons because there's 7 orbitals. 14. So you can remember that because when you go down here, if you count from left to right across F, you'll get either 13 or 14, something like that, depending on how the particular periodic table is drawn. Which, okay, you know it's not going to be 13 because that doesn't make sense with 2 electrons per orbital, so it's going to be 14. Okay, so now after you do that, then you come back up here and then you fill the 5d. If you count across left to right, you'll see there's 10 electrons that can go into there. So we say 5d 10. And now the home stretch. So now we fill into the 6p just 2 electrons. So then we'll say 6p2. Okay, so now this is the answer for the ground state electron configuration of lead, using the noble gas shortcut and using the periodic table to figure that out. Okay, for the pre-quiz question, I'll let you have this one. What's the ground state electron configuration of selenium, which is atomic number 34? Now, another question we can ask that kind of relates the two between electron configurations and quantum numbers is this one. What are the possible quantum numbers for the outermost electron, or the highest energy electron in chlorine? Okay, how would you go about doing this one? I mean, I encourage you to pause the video and try it yourself and then listen to my explanation. So chlorine has 17 electrons. Now, when you do the electron configuration of it, it'll come out to be something like this. And so when you do this, you'll see that the last electron is added to the 3p orbital. So that's the one we're going to deal with. We're going to deal with the 3p. So now we just have to think of the quantum numbers for the 3p orbital. So we've changed our question in a way to the question we actually need to answer. Okay, for the 3p, you have n equals 3, and since it's a p orbital, L equals 1. Now, there's 3 different p orbitals, which is a good hint that your m sub L is going to have 3 different values. How do I know there's 3 p orbitals? Well, that's something I've committed to memory long ago. You can also figure that out from the periodic table. But since there's 3 p orbitals, the m sub L goes from -1 to +1 in 3 steps. Now, then you always have to include the spin quantum numbers, -1/2 or +1/2, because without it, you wouldn't be able to put 2 electrons into an orbital. So, this answers the question. What are the quantum numbers for the last electron in chlorine, or the highest energy electron in chlorine? Okay, last example, and I'll let this one come up as a pre-quiz question for you to do also. What is the ground state electron configuration in the chloride anion? So one big hint here is, since it's the chloride anion, it's going to have some different number of electrons from the just neutral atom chlorine, and you've got to figure out, is there more or less electrons? And then once you figured that out, then you just fill the more or less electrons like you would normally fill electrons. Alright, last thing in this video is to talk about excited states. So, and this connects us back to the Bohr model discussion we were having earlier. When your atom absorbs energy, an electron is promoted to a higher energy level. And now that we know a little more about energy levels, when you have more than one electron, you have more options, right? Because the 2s and the 2p are no longer the same energy, so you have all kinds of different options here. Thus, if you look at the absorption or emission spectra of the heavier elements, you have a boatload of different lines, as opposed to hydrogen, which just has 4. In the visible region of the spectrum. And yeah, I had to add a voiceover because I couldn't let that inaccuracy go when I was editing. Okay, so in this case, the lithium atom in the ground state on the left, if it absorbs a photon of the energy associated with 671 nanometers light, then it'll promote this high energy electron to an even higher state. This is called an excited state on the right. And you can write the electron configuration for this if you want. You can say in the excited state, the electron configuration is 1s2, 2p1 in the first excited state. Now this could go to the second excited state. It could jump up to the 3s, or the 3p is then the third excited state. So once you know excited states and how to do ground state electron configurations, this little extension is pretty easy to realize once you put these two concepts together. Okay, and that's it for now. So thanks for your patience sitting through a long video again, and hopefully now you're ready to go determining electron configurations of elements. Thanks for watching.